June 2025. Without warning, satellites detected an unexpected uplift deep beneath California, enough for USGS to sound an urgent alert across the Sierra Nevada, Central Valley, and the coast. Evidence mounted. The ground shifted centimeters in days, raising questions about what lies below. Is this the first signal of California's crust preparing for catastrophe, or a clue to an older buried threat we have missed all along? The answer starts with the official alert that upended the normal pattern and forced scientists to look deeper. The words arrived in the early hours. Rapid, unexplained crustal uplift detected. Ongoing ground movement confirmed by satellite and GNSS. All scientific teams to elevated monitoring status. Further updates to follow as data is verified. The official notice, timestamped June 14, 2025, carried the USGS seal and named the Sierra Nevada, Central Valley, and coastal corridors as regions under immediate scrutiny. For most, this was the first time hearing of a large-scale crustal shift that did not come with the jolt of an earthquake or the warning rumble of volcanic activity. Phones buzzed, news tickers flashed, and local emergency managers fielded urgent calls from city halls and school boards. The USGS, usually measured in its public statements, chose language that left no room for doubt. The alert described a centimeter-scale upward displacement detected over several days, affecting an area home to more than 20 million people. The document avoided technical jargon, instead stating plainly, "This movement is not associated with any known earthquake or volcanic event. The cause is under investigation. There is no immediate hazard, but ongoing monitoring is critical." Dr. Ben Carter, a senior USGS geodesist, took to a live briefing within hours. He said, "We are looking at a broad, persistent uplift, not a single shock or tremor. Our satellite partners at NASA confirmed the signal. This is not routine. We are deploying more sensors now." His words, calm but unmistakably serious, echoed across local news and social feeds. In Sacramento, county officials debated whether to activate public alert systems. School districts in Fresno and Merced asked for guidance on earthquake drills. Calls poured into the USGS Public Affairs line, many asking the same question. What does this mean for our homes, our water, our safety? The scope of the notice was unprecedented. The affected zone stretched from the southern Sierra foothills, across the Central Valley farmland, to the edge of coastal cities. Maps accompanying the alert showed shaded swaths where the ground had lifted by as much as 2 centimeters in less than a week. For comparison, normal tectonic drift in California measures just a few millimeters per year. Scientists from Caltech and Scripps joined the rapid response, reviewing INSAR and GNSS data in real time. Dr. Evelyn Reed of the NISAR mission said satellite radar data show ground movement near the San Andreas, some from aseismic slip, some from deeply rooted processes we are still deciphering. For residents, the language of the alert was both clear and unsettling. Unlike a weather warning, this notice contained no timeline for resolution, just a promise of updates as more data arrived. The USGS urged the public to follow official channels, prepare standard earthquake kits, and avoid speculation until further notice. As the day unfolded, the official alert had done its work. It forced a pause across the state, turning the ordinary into a waiting game. The question was not just what had happened, but what might come next, and how deep the mystery beneath California really ran. Satellites poured in from multiple sources. Sentinel-1, ALOS-2, and Cosmos SkyMed, each offering a unique window into the ground's subtle movements. Analysts at NASA's Jet Propulsion Laboratory began stitching together stacks of radar images using the SBAS technique, a method that transforms hundreds of satellite passes into a time-lapse of the Earth's surface, precise to within a few millimeters. The maps showed a broad, dome-like uplift stretching from the Sierra foothills across the Central Valley and into the coastal ranges. In some areas, the ground had risen by as much as 2 centimeters in under a week, a pace that normally takes years, not days, to register. The next step was cross-checking these findings with California's dense network of GNSS stations. Each station, anchored to bedrock and recording vertical and horizontal motion around the clock, showed the same story. Abrupt upward offsets of 18 to 22 millimeters, matching the satellite trends almost exactly. Where the INSAR maps displayed color-coded swells, the GNSS data traced sharp jumps in vertical position, confirming the event was neither a processing error nor a fleeting atmospheric illusion. Fault overlays revealed a pattern that caught the attention of every geodesist in the room. The uplift was not random. It tracked along the San Andreas, the Garlock, and the Eastern Sierra frontal faults, lines that have defined California's seismic history for generations. Yet this movement was aseismic, unfolding in silence with no quakes or tremors to explain the energy release. NASA's ground team ran additional simulations, stripping out weather effects and sensor noise, but the uplift remained. The data's internal consistency, backed by 3 independent satellite missions and dozens of ground stations, left little doubt. The crust was on the move. Dr. Priya Malhotra, a senior geodesist at the Jet Propulsion Laboratory, put it simply, "We are watching the ground breathe in real time, except this time, it is not following any script we have seen before." Her team published the first composite deformation maps to USGS and Caltech partners, each frame revealing the uplift's reach and rate. The SBAS processing pipeline flagged the event as high confidence, with uncertainty margins below 5 millimeters for most of the zone. As word spread among scientific teams, the focus shifted from detection to understanding. Was this a slow slip event deep within the crust, a sign of fluid migration, or something else entirely? For now, the only certainty was the signal itself, a measurable, verified vertical change, unfolding beneath the feet of millions. The satellite maps, overlaid with fault traces and population centers, transformed a technical anomaly into a story with real-world stakes. For the first time, the mystery beneath California had a face, etched in radar lines and ground station graphs, waiting for an explanation. Beneath the surface of California, the story of today's ground movement stretches back tens of millions of years, to a time when the crust itself was being shaped by lost tectonic giants. Deep under the Sierra Nevada, geophysicists have mapped a zone where the lower crust appears to be peeling away, a process known as lithospheric detachment. This is not a slow, gentle separation. Tomography scans show a sharp boundary at depths of 70 to 100 kilometers, where dense ancient rock is sinking into the mantle while lighter material rises to replace it. The geometry of this detachment matches the broad uplift now seen at the surface, with the dome-like swell echoing the shape of the peeling layer far below. The roots of this weakness trace back to a vanished tectonic plate. For decades, structural geologists debated the existence of a so-called ghost plate, a slab that once slid beneath California, then broke apart and disappeared. Evidence for this lost plate comes from a chain of faulted basins stretching from the Mojave to the coast, and from the chemical fingerprints found in volcanic rocks and deep-sea sediment cores. Density calculations reveal a missing mass beneath the Central Sierra, a gap where the ghost plate once pressed upward against the overlying crust. Animations produced by tectonophysicists bring this hidden world into focus. Cross-sections reveal how the Sierra Nevada's uplifted block is balanced atop a zone of weakness, its base cut by the detachment. The overlying crust, no longer held down by the dense ghost plate, has rebounded upward, creating the uplift now recorded by satellites and GNSS stations. Fault geometry in the Central Valley and coastal ranges further links these deep processes to today's surface changes, with basin shapes reflecting the scars of ancient subduction and detachment. This structural model explains why the recent dome-like uplift is so widespread and uniform. The ground is not simply swelling from below, it is responding to a deep, ongoing reorganization of the crust. Zones of weakness mapped by seismic tomography align with the uplift's footprint, suggesting that the legacy of the ghost plate still shapes how California's surface moves. As scientists continue to refine these models, the connection between ancient tectonic events and modern ground movement comes into sharper relief, offering a new lens on the underground forces at work beneath California. These insights change how we interpret signs of future activity and why monitoring at depth matters. Inside the Scripps Core laboratory, rows of sediment cylinders stretch like time capsules, each one drilled from the floor of California's offshore basins or pulled from beneath the Central Valley. These cores are more than mud and sand. They hold the physical record of upheavals that have shaped the region over tens of thousands of years. Marine geologists begin by slicing the cores lengthwise, exposing layers that alternate between calm deposition and sudden jumbled chaos. Event beds, distinct bands of broken shells, coarse gravel, or volcanic ash interrupt the regular rhythm, hinting at moments when the crust itself convulsed. To decipher what triggered these disruptions, scientists turn to mineral diagnostics. Under high-powered microscopes, they search for shocked quartz, grains marked by microscopic planar features that are evidence of pressures far beyond what normal tectonics produce. In a core from the Monterey submarine fan, a layer at 490 centimeters depth reveals quartz grains etched with these telltale lines. Electron microscopy confirms their structure, matching the patterns produced in laboratory shock experiments. The presence of shocked quartz here is rare and significant. It signals an event powerful enough to fracture the deep crust or even result from a massive impact. Determining when these upheavals happened requires precise dating. Radiocarbon analysis of organic material nestled just above the event layer in the Santa Barbara Basin core returns an age of 13,200 years, with an uncertainty of about 3 centuries. In the Monterey fan, argon-argon dating of volcanic ash mixed with shocked quartz pins the event to roughly 16,700 years ago. These numbers are cross-checked with paleomagnetic data and tephrochronology, tightening the window of uncertainty. Layers like these, sometimes only a few centimeters thick, are scattered throughout California's stratigraphic record, each marking a discrete moment when the crust shifted violently and left a signature in the sediment. Not every claim holds up to scrutiny. Some supposed catastrophe layers lack direct dating or show quartz features formed by slower tectonic grinding, not sudden shock. But where mineral diagnostics and radiometric ages align, the evidence is hard to ignore. California's crust has a history of abrupt, extreme movement. These findings support the idea that today's uplift may be part of a recurring cycle, echoing the ancient pulses captured in the cores. The physical proof, cataloged in lab notebooks and peer-reviewed studies, grounds the current mystery in a much longer story, one written in grains of quartz and bands of displaced sediment, waiting for the next chapter to be revealed. Deep within California's crust, the first hints of trouble rarely come as a sharp quake. Instead, scientists trace faint trails of tremor, bursts of low-frequency shaking that ripple quietly through the lower crust, often at depths of 20 to 35 kilometers. These tremor signals, cataloged in detail by the Southern California Earthquake Center, migrate along fault zones, sometimes over days or weeks. What sets them apart is their relationship to fluids under extreme pressure. As geophysicists model the data, a pattern emerges. Tremor swarms tend to follow the rise of pore pressure, where water or gas seeps into faulted rock, weakening barriers that would otherwise keep faults locked tight. Seismic networks and pressure models now reveal that these deep signals often precede larger, more damaging events at the surface. When pore pressure climbs, it can trigger slip along hidden fault planes, setting off a chain reaction that sometimes ends with a major earthquake. Dr. Alicia Torres, a seismologist at the Southern California Earthquake Center, describes it this way: "Tremor is the sound of the crust preparing to move. It is not the main shock, but it is the warning, the system's way of telling us that stresses are shifting below our feet." Recent catalogs show tremor swarms clustering near the Garlock and the creeping sections of the San Andreas, their migration mapped in real time. Pressure increases modeled in these zones align with satellite-detected uplift, raising the possibility that today's silent movement is not just a passive response, but the early stage of a much larger process. The weakness mapped by geodesists is now a dynamic threat, as fluids activate faults that were once thought dormant. As the story moves forward, the question becomes not just where the next tremor will strike, but whether these deep whispers will soon give way to something far more powerful. The risk tied to California's underground movements becomes clearer when looking at how faults can interact. In 1992, the Landers earthquake sequence began with a magnitude 7.3 shock in the Mojave Desert, but what followed caught scientists off guard. The main rupture jumped across several faults, triggering a domino effect that extended for more than 70 kilometers. Just hours later, the Big Bear Fault gave way, and aftershocks rippled outward. This event showed that stress does not stop at one fault line. Under the right conditions, it can leap across gaps, linking separate faults into one extended rupture. Dynamic rupture models now simulate these chain reactions, using real geologic data to estimate how far and how fast a rupture might spread. Some scenarios project single-event ruptures stretching over 300 kilometers, especially if deep fluids have weakened fault barriers. The Southern California Earthquake Center has developed a tiered matrix for these possibilities. Low probability, high-impact events sit at the top, while more frequent, moderate ruptures fill the lower tiers. Recent uplift mapped along the San Andreas and Garlock faults fits into these models as a potential trigger. If stress transfer lines up with a critical segment, the result could be a cascade, one rupture setting off another, amplifying the hazard zone far beyond the initial epicenter. The Landers sequence stands as a reminder. California's faults are not isolated threats, but parts of a connected system, capable of producing surprises on a regional scale. California's emergency managers work behind the scenes to keep the public a step ahead of the next surprise. County Office of Emergency Services teams, known as OES, rely on real-time feeds from the USGS, the statewide Shake Alert system, and their own network of seismic monitors. Shake Alert, now fully operational across California, can deliver an earthquake warning to your phone or smart speaker seconds before strong shaking arrives. Signing up for these alerts is as simple as enabling notifications in the MyShake app or checking with your county OES website. Preparedness starts at home. Officials recommend a checklist: secure heavy furniture, anchor water heaters, keep a flashlight and sturdy shoes near your bed, and have a go bag ready with water, snacks, and essential documents. Know your local evacuation routes and designate an out-of-state contact for your family. OES managers stress the importance of trusted information. Follow official feeds like at Cal_OES, at USGS_quakes, and your county's emergency Twitter or Nixle alerts for accurate updates. Avoid rumors and unverified sources, especially in the hours after any alert. Staying informed and ready won't stop the ground from moving, but it can make all the difference when seconds count. California's crust remains restless. Satellites now capture shifts that were invisible just a decade ago. As our technology sharpens, so does our responsibility. 39 million lives depend on what we learn before the next rupture. The ground is never truly still. In a place built on movement, awareness is our only certainty, and the next warning may already be underway, deep below our feet.